All right, hey everyone, welcome to the Ice Giant System seminar series. Usually Mallory Kincheck is here to kind of host and moderate the conversation, but she's out this week, so I'm kind of filling back in for this position. But we usually swap back and forth occasionally, depending on how our schedules allow for it. So you've got me this week. So I'm just going to introduce our speaker, Conor Nixon, and then I'll let him kind of take it away. So Dr. Conor Nixon is a planetary scientist at NASA's Goddard Space Flight Center, or GSFC, in Greenbelt, Maryland, and head of the Planetary Systems Laboratory. From 1997 to 2007, he was a member of the Cassini Mission Science Team and deputy principal investigator of Cassini's Composite Infrared Spectrometer, or CIRS, built at Goddard. His research interests range across the atmospheres, surfaces, and interiors of planets and small bodies in the solar system, with a particular focus on the atmospheres of the outer planets and their ocean world moons. Prior to joining NASA, he was a research scientist at the University of Maryland, College Park. Originally from the United Kingdom, he earned a BA in Natural Sciences from the University of Cambridge, an MS in radio astronomy from the University of Manchester, and a PhD in atmospheric and planetary science from the University of Oxford. And outside of work, he likes to ski, hike, run, and scuba dive, which is pretty awesome. So yeah, go ahead and you got your slides up. We can see you, we can hear you. And so I'll turn my camera off just so that the focus is kind of more on you for this. But yeah, go ahead and take it away. We're happy you're here.
Okay, great. Well, thanks, Jody, for that introduction. And also to Mallory, who's not here, but for inviting me to give this talk. I'll probably take questions at the end, I think, unless there's burning questions in the middle, but that will enable me to get through the material. I'll try to allow time for questions at the end. So Mallory wanted me to talk about spectroscopy of the ice giants in the thermal infrared, aka mid-far infrared. I think it's a really important topic. It's something I know a little bit about from being on Cassini. I've done a lot of work on Jupiter and Saturn systems, maybe a little bit less on the ice giants. But I've worked a lot with Voyager data as well, and ground-based spectroscopy. So hopefully I can provide some useful insights for people that are thinking about these missions in the next couple of decades to go to hopefully Uranus and maybe Neptune as well. So what I'm going to talk about today, give some examples, first of all, about what we can do in the thermal infrared for the ice giants. When I was putting together this talk, I realized that there was actually a lot more observations and telescopic observations that I could ever fit into one talk. So it's really just going to be some illustrative examples. I'm not aiming for completeness here, but hopefully some useful examples. And I'll mention, by the way, there is an excellent review paper which you should all go and read on this topic by Mike Roman about the far infrared spectroscopy of the giant planets. It came out, I think, last year. So, and you'll see some of the material in this is drawn from his paper. And then I'm going to switch over to kind of future science goals, what we can do that hasn't been done yet, and how we can address those with instrumentation. Again, it'll just be a very brief look at a very big topic, and then some of the mission opportunities and conclusions. So let's see. Let's see what we can get through today. So first of all, just a kind of comparison here, and this is from Mike's paper, to show the on the left here the thermal structure of the 4 giant planets, and then on the right the emission that you get, and this is in brightness temperature. And of course you can see Jupiter is the warmest, Saturn's the intermediate, and then surprisingly Neptune turns out to be a bit warmer than Uranus. But the tropopause temperatures of Uranus and Neptune are very cold. We're talking about mid to upper 50s in Kelvin, and that provides a real challenge for detecting their emissions in the mid-far infrared, just because of the background that we typically get from our telescope optics and detector background and so on. Even though we want to look at this part of the spectrum because they do have Planck functions that are peaking at long wavelengths. You can also see from this spectrum on the right that there's lots of interesting information in the far infrared spectrum. There's emissions of hydrocarbons, there's emissions of H2 and CO2, water, and so on. So there's lots of really interesting information here. The question is being able to get enough sensitivity to pull it out of the spectrum. So a few examples of previous observations. I think one of the key, certainly not the first, but one of the key observations was with Voyager 2, which of course went to Uranus, visited Uranus in 86 and Neptune in 89. Voyager carried on board a far infrared spectrometer called IRIS that was led by Goddard here. 50 centimeter telescope and thermopile detectors running at about 200 Kelvin. And this just really illustrates some of the challenge in trying to detect flux from these giant planets. You can see here the spectrum from about 200 to 400 wave numbers, or if you're used to microns, that's about 25 to 50 microns. And this was the only part of the spectrum where we were able to actually see emission above the noise level. And you can see on that upper spectrum there that towards the left and right, it's really just degrading into noise pretty rapidly. So very, very little part of the spectrum was able to be detected with any useful amount of signal to noise. But with that part of the spectrum that was detected, we were able to, to derive some information about the temperature profile of the atmosphere. And again, one of the advantages of having the spacecraft as opposed to, say a telescope on the Earth is that you're able to get that nice spatial resolution. There's also some information that was gained about the hydrogen to helium ratio, which is actually still a topic of active work. And then at Neptune, something similar here on the left, you can see some kind of brightness temperature maps that were made. And on the right, derived temperatures from the spectrum at 350 and 250 inverse centimeters. This is actually, I think unfortunately the x-axis was cut off, but this is actually showing the variation in temperature with latitude. So the nice thing here, being able to determine the temperature profiles close up. Another interesting finding from the Voyager data was the hydrogen ortho-para ratio. So hydrogen comes in two spin states. You've got spin parallel or spin anti-parallel. And due to quantum selection rules, these actually translate into the even numbered J states or rotational states are with the para-hydrogen, and the odd J states are with the ortho-hydrogen. So by actually doing spectroscopy, and you can see here on the left, this is actually Jupiter data. It's way too nice for Uranus Neptune data. We can see these S0 and S1 transitions of hydrogen, and that enabled us to actually derive the ortho-para ratio as a function of latitude, which you see on the bottom left there. Why are we interested in that? Well, at high temperatures, particularly in the deep atmosphere, we expect that the ortho to para hydrogen is going to basically be in a 3-to-1 ratio. That's what we call normal ortho para hydrogen, which is just due to the proton spin statistical weights. But as that hydrogen rises up in the atmosphere and gets to colder temperatures, and particularly in the presence of magnetic fields, it can actually translate into more of a 1-to-1 ratio. So by actually looking at the ortho to para ratio as a function of altitude, we can get information on vertical transport. And you can see here on the right, there was an attempt to also do this with the Neptune data from Voyager, but just due to the noise in the spectrum, we weren't able to get very far, except to say that none of the models really fit particularly well. And that shows that, even just playing around with the ortho-para ratio doesn't seem to be enough to fit the spectrum there. So there's probably other things going on as well. But something to bear in mind, in principle, we can get information about vertical transport by looking at this hydrogen orthopower ratio, and it tells us information about how long the hydrogen has been in its present altitude. Looking at some ground-based data this is from the early 90s. This is from RTF IRShell. This is from Neptune. You can see on the left some part of the methane spectrum and deuterated methane spectrum. And then in the center there, at slightly longer wavelengths, around 12 microns, you can see the ethane and acetylene towards 13 microns. Beyond that part of the spectrum, due to the ground-based caloric absorption of CO2 at 15 microns, we can't go any further, into the red. But using the measurements that were possible, you can see there's a fit here, which enabled the determination of these hydrocarbon ratios, but without any spatial information. And another example, slightly later, again, RTF with a different instrument, more modern instrument, was able to get slightly better data. Here you can see Neptune on the left and Uranus on the right. And again, illustrating that because Neptune is warmer, there's a couple of differences from Neptune to Uranus, even though in many respects they appear like twin planets. Neptune being warmer, especially having a warmer stratosphere, and apparently many more hydrocarbons in its stratosphere, has two effects. Basically, there's more thermal emission and there's more gas there, so you get much stronger emission lines, whereas on Uranus you're really struggling to be able to detect these gas bands. And moving on to space telescopes, so beginning in the late 90s, I mean, there were some earlier infrared telescopes, particularly beginning in the late 90s through to today. There's been a number of really important observatories that have been sensitive to the mid and far infrared, and even going further into the sub-millimeter part of the spectrum. The ISO and Spitzer telescopes from ESA and NASA, which were smaller telescopes, sort of half a meter to a meter class telescopes, and then a bit later, Herschel, and eventually today Webb, with much improved sensitivity and in some cases, particularly with Herschel, able to go really, really far into the sub-millimeter part of the spectrum. So we're going to look at some results from those, again, just a kind of representative cross-section. Beginning with ISO here, one of the important discoveries from ISO at the far infrared, around 40 microns, you can see here that there was water lines detected on both Uranus and Neptune. And that indicated that there's got to be an external source of oxygen, simply because the troposphere, tropopause cold traps on those planets are so cold that there's really no chance of getting water coming from below and coming through that 55, 58 Kelvin cold trap and getting into the stratosphere. So the fact that these emission lines are detected in the stratosphere indicates that there is external supply of oxygen, water, and even CO2 on Neptune. Whether that is due to infalling ring material, cometary material, or some mixture of those is still a topic of debate. But being able to detect these gases has had important implications for our understanding of their atmospheres. And then on the right here, you can see some hydrogen lines, both hydrogen quadrupole lines and also HD lines, rotational lines here. And by being able to measure, again, these lines in the lower stratosphere has enabled us to make attempts to measure the hydrogen D to H value, which is a very important constraint on planetary formation. Of course, we know that the D over H in gaseous H2 is much lower than we typically find in icy materials. So by measuring the D over H and comparing that between the various giant planets, we're able to get a model of the various fractions of icy material versus gaseous material that formed those planets, and hence provides constraint on their formation scenarios. And then moving on to Spitzer, a really sensitive spacecraft here. You can see on the left some of the gases that were detected here. Again, with the Space Telescope, the big advantage being that we now get the whole spectrum and we're not cut out by any regions of caloric absorption. So you can see here a Uranus spectrum that was modeled by Orton, taken in 2007, and then the publications were on 2014, showing that there was various hydrocarbon detections and other gases in the atmosphere. This enabled us to make new detections of heavy hydrocarbons. There was a tentative detection of methyl radical, and the ability to measure the vertical temperature profile by modeling the hydrogen continuum. And here an example of methane far infrared rotational lines with Herschel that were used to derive the methane vertical profile on Neptune. So again, here 3 panels showing methane lines. And then in the lower right, you can see the implied methane profile, showing that the amount of methane in the troposphere, again, on Neptune here, is quite unexpectedly high. And it seems to be much higher than we would expect to be able to get through the Chopopause cold trap. The reasons, again, are up for debate in terms of whether there is the ability for really, really vigorous convective events, perhaps at low mid latitudes being able to pump methane into the stratosphere, or whether there's something going on in the polar regions, which has been proposed with a sort of warm, elevated chopopause that actually enables more of the methane to just diffuse upwards into the stratosphere, and then to be distributed around the entire planet. So this high methane in the stratosphere, again, a very, very interesting point on Neptune, and quite different from Uranus, as we'll see later. And with JWST, we do have some really cool images of the ice giants. I believe there's nothing yet in publication about their spectra, although there's been some conference presentations of that, I think particularly by Mike, Roman, and others. So we're still waiting to see what's going to come out of the spectroscopy with particularly with MIRI, but it should be really spectacular. So sort of TBD, watch this space. So moving on from what's been done in the past to what do we want to do in the future, I tried to make a list here of some of the questions that we can attempt to answer here for Uranus and Neptune using thermal infrared spectroscopy. I'm not going to read this all out, but there's important measurements that we can make, both of the gas abundances, the gas vertical profiles, temperature profiles. Of course, we'd like to map those across both latitude and time. We like to look for correlations with clouds that we see in the deep atmosphere. Being able to measure this orthopower H2, as I've mentioned before, gives us a measurement of mixing. And we can also get the sort of information perhaps from disequilibrium species, such as methane. And then, isotopic ratios, elemental ratios. Some of this work is perhaps arguably better done by having a probe where you can really get into the deep atmosphere and measure the well-mixed gases of the deep atmosphere. However, if we were not able to get a probe, or if we have to wait, we can get this information also by remote sensing, and that provides an alternative route to getting isotopic and elemental ratios. And there's some nice papers already on this if you look at the work of Lee Fletcher and others. So some of the measurements that we need to make to get these are things like temperatures, wind fields, gas abundances, isotopic and elemental ratios. And we can do that again through the far infrared using continuum emission, line emission. Some of the wind fields are perhaps best done with very, very high resolution heterodyne spectroscopy, such as submillimeter heterodyne. And you can see some work's being done using ALMA. Could also be done using a submillimeter instrument on a spacecraft, but potentially also through infrared heterodyne techniques, which has been demonstrated, for example, using the HIPWAC on RTF. And illustration here from the work of Moses et al. Showing the cloud layers in particular that we expect to form at different altitudes in the atmospheres of the ice giants, and illustrating that we want to be able to find out what these optical depths are to get the gas abundances, relative humidities, which is going to tell us about the composition of the deep atmosphere and also the mixing which is going on. As we know, Uranus and Neptune really different in terms of their obliquity, with Uranus being kind of almost pole facing at times, whereas Neptune being more equatorial facing. So that has big implications for the differences in the way their atmospheres are circulating. Looking at some of the gas abundances here, again, from the work of Moses et al., a nice review paper showing both the data points that are measured, but also the models from Joules' photochemical model. Really dramatic differences between Uranus on the left, Neptune on the right. You can see, for example, the methane, which is the green, really extending at fairly high abundances into the stratosphere on Neptune, whereas on Uranus, really being undetectable in the stratosphere. Also, really big differences by orders of magnitude in the amount of even CO, which is not expected to, which condenses at much colder temperatures than methane, but also showing quite big differences in abundance, and many of the other hydrocarbons as well. So the takeaway message here is that Uranus and Neptune, despite being superficially similar, really have differences in their atmospheric composition, which is telling us something about perhaps both external and internal sources of material that's getting into the stratosphere. So in terms of instrumentation, the challenge for the mid-far infrared is the long wavelength nature of the emission on Uranus and Neptune, which you can see here again from Mike Roman's paper, showing that these Planck functions for Uranus and Neptune are pushed out to 40 microns or so compared to Jupiter and Saturn. And that really means that we have different technologies that we need to use. There are fairly standard photon counting detectors, which are great up to 15, even 20 microns. But then beyond that, the technologies really change, and we need to go to thermopile detectors and really look at making sure our optics are really cold so that we can get the sensitivity which we were lacking, as you saw earlier with Voyager Iris. This unfortunately slightly unclear, but this is the optical diagram of Voyager Iris, indicating that we had this 50 centimeter primary telescope, and then this was fed into an FTS, or Fourier transform spectrometer for the back end. But with only one detector, it was really limited in some ways in terms of what it could do, both in terms of spatial resolution and spatial mapping. So going forward, we'd want to, if we were going to put an instrument like this on a mission to Uranus or Neptune, we want to be able to update that with better detectors and being able to work more quickly and with more sensitivity across the whole spectrum. And at the same time, we have these challenges in trying to keep the overall instrument small and lightweight and low power, which are perpetual concerns. So what materials can we use for telescope design? Traditionally, beryllium has been one of the best options. Beryllium was used for the Voyager Iris half-meter telescope, which was gold coated to improve reflection. And this technology, which was developed in the late 70s or mid to late 70s for Voyager, in fact, eventually made its way onto JWST, and you can see the main mirror of JWST also using this beryllium, gold-coated beryllium technique to really for a combination of reasons, including the fact that beryllium is a really lightweight material, not always easy to work with, but does have good optical properties. And other materials that we can use, different types of silicon carbide glass may be good alternatives going forward, but have their own challenges in terms of machining and so on. Optical design, there are trades that we can consider, and this is from a JPL study published in 2017 showing two different optical designs with an on-axis and off-axis telescope design. Really up until recently, we've been limited in terms of going with symmetric on-axis optics, just in terms of optical design and machining, and so on. But with the updates in computer modeling of optical ray tracing, and especially the updates in being able to machine off-axis mirrors, have really given us a lot more flexibility to do things that were not possible before. So that gives us the example you see on the right here with the off-axis telescope design. It's a little bit bigger, but does in some respects have better stray light control. So there's more details of that in the paper by Braggio et al. An example here of a Goddard designed telescope, 30-centimeter telescope here for a far infrared radiometer that was studied during the last decade, again for potentially for use on the outer planets. Detectors are also a very important area. We would love to be able to get detectors that are more sensitive than the ones that we had on Voyager. Technologies have not always moved forward as quickly as we would like, but you can see here some examples on the left here of superconducting bolometers and cryocooler technologies that are needed to get these down to operating temperatures. And then on the right here, a thermopile, uncooled thermopile array, which is another alternative with a slightly lower D star, but also with the ability to make smaller detectors than we had at the time of the Voyager era, and also to make these into arrays. Example here of some of the readout that was developed for reading out these thermopile detectors with kind of multi-channel readouts that would enable us to have multi-pixel detector arrays as opposed to just single pixel detector arrays that we had before. Another type of technology here, this is a high TC or high transition temperature superconducting detectors with this yttrium barium copper oxide type technology, which is intended to work at around 80 kelvins, so quite a bit warmer. And this is something that is still under development for use on future missions, and I think has not yet been fully demonstrated in a space environment, but potentially offers really nice high sensitivity compared to the previous detectors that we've been able to put on spacecraft. So what mission opportunities are there? There was this ice giant study report came out in 2017, which in some ways fed into the 2022 decadal survey. There was a lot of trades that were studied here. It's a very large report if you want to go and take a look at it. There was a possibility of having a mid to far infrared spectrometer on here. It was one of many instruments that were potentially included on the payload. Although, as you'll see here on some of the mission options, many of the smaller mission options didn't include the mid-infrared instrument, which was only included on a sort of like a larger spacecraft option. So having gone and looked at some of the recent mission proposals, including things like the recent Neptune Odyssey study, we see that mid-far infrared spectroscopy is not always making its way onto the payload. There's perhaps a concern that these instruments are kind of larger, heavier. They need larger telescopes with the cryocooling, and they're power hungry, and that's maybe causing them not to be always put on the payload. But I think that it is a really important part of the spectrum, as you can see from the Planck functions that I showed earlier, and it really offers really different type of science than you're going to get in the near infrared, looking at the reflected sunlight in the deeper atmosphere, or going to the submillimeter, where there's also really great science to be done, particularly with heterodyning techniques, for example, for wind measurements, but not the ability to measure all of the same gases. And I think this is something that's sometimes overlooked, is that in the submillimeter, you're really constrained to gases that have asymmetric molecules with a permanent dipole. So you're never going to see gases like methane, acetylene, ethane, diacetylene in the submillimeter part of the spectrum, because they don't have a permanent dipole, so they cannot produce a rotational spectrum. So in conclusion, I'm going to wrap up and say that the ice giants push the peak of their thermal radiation out to around 40 microns. That's really pushing us out into that mid-far infrared part of the spectrum. And to be able to use all the information that's there, there's really no alternative to having a spectrometer that operates in that part of the spectrum. And it can achieve a wide range of science goals, including particularly looking at the vibrations of molecules, giving us gas abundances and temperatures, giving us perhaps implied winds from thermal wind equation, dynamics, as we saw from hydrogen orthopara, and isotopic and elemental ratios at certain altitudes, certainly. But unfortunately, these type of instruments are not being included widely. I'm seeing on ice giant Strawman payloads. So I think that's an overlooked, quite important part of the EM spectrum. And using space telescopes, we can't do it all. We do need the up close and personal look with spacecraft. So I really hope that this is something that will receive more attention going forward for consideration on future missions. And with that, I'm going to wrap up and leave some time for your questions. Thank you.
Yeah, excellent. Thanks so much, Connor. I'm clapping over here. I know there's a reaction for like the clapping. I see some people found it. Okay, good. I know there's a way to do it. So, oh, here it is. There we go. Yeah, everyone's okay. Excellent. Yeah, that was a really great talk. Thanks, Connor. I think a lot of times, it can be easy to get, into the weeds with the science, but actually making sure that we've got technology and instruments to measure things so that we can do the science is really important. So I'm glad you focused on that in this talk. I think that's an important conversation, and especially with the Uranus flagship workshop happening next week. I think it's certainly timely. So yeah, that was really great. So folks can feel free to put their questions in the chat if they would like. Even better if you'd like to use the raise hand feature and just turn your camera on, turn your mic on, and ask Connor yourself. That would also be great. At least on my Zoom, it's under the react button on the bottom, and there's kind of this raise hand. I don't know if everyone has the same version. Mine updated recently, so I don't know if it says the same thing everywhere, but there's a thing at the bottom that allows you to raise hand. And so, feel free to start getting your questions in. So it looks like Mark has his hand up. Yeah, go ahead, Mark. Make sure you unmute.
Whoops.
There you go.
Yeah, great. Thanks. Thanks, Connor. Very good talk. I just wanted to give you or ask a question about the new technology instruments. One of the selling points of the Uranus flagship has been, we could do it with no new technology. And so, what happens if we use, as in the Decadal Survey study report, diviner type technology for this spectral region. You know, how do you feel about that?
Yeah, thanks, Mark. Good question. So, you know, diviner, as I understand it, is not a spectrometer, right? It's a filter instrument. So it's a filter mid-infrared mapping instrument. You can probably remind me, but it's got like a, you know, six or 10 spectral bands, something like that. And so that's not spectroscopy, right? So we can place those spectral bands on interesting parts of the spectrum, you know, perhaps taking narrower and wider regions. We can put things maybe on top of methane, or on top of, you know, top of ethane, top of continuum. It's always a trade, right? In terms of what are your most important science questions and how much resources do you want to devote to those? You know, people may come out and say, well, you know, JWST, you know, can map hydrocarbons on the ice giants. You know, not very well. You know, nice spectral resolution, really great sensitivity, but spatially, you know, pretty sucky. You know, we're talking about, let's see, so Uranus is what, 3.3 arc seconds, and Neptune about 2.2 arc seconds. So once you get out to 15 microns, I think with JWST, if I remember correctly, you're basically out to about 1 arc second spatial resolution. So, you know, you're getting like, you know, a small handful of points across the planet. So you're not able to really measure in detail things like, you know, gases confined into polar vortices, especially things like jets, you know, like narrow latitude jets and things like that. So I think there's a place for spectroscopy. The problem about spectroscopy is that, you know, the higher resolution you go to, you're putting your photons into smaller and smaller bins. So you're always dealing with a photon problem. There's how many you can scoop up in your telescope versus how many little bins you're going to divide those into at the end of the day, and how much noise you have to deal with. So, you know, it may be that, you know, we don't want to do, you know, super high resolution spectroscopy. Yeah, I probably should have put in a slide to show the differences between FTS and grading spectroscopy. I think one of the really nice things about an FTS, and, you know, I'm biased, of course, because I've worked on FTSs for most of my career, is that you can change the spectral resolution. So with a grading, you're stuck, right? Your grading it's got the blaze that it has, and that's what you've got. And if you want to do something else, you can bin your data afterwards. But with an FTS, you can actually change the resolution just in terms of how far you scan your secondary mirror, or your movable arm of your FTS, and that enables you to do low resolution versus high resolution and change the amount of scan time, and you know, do the science that you want. You've got that flexibility, so it's a bit of a so there's real nice advantages there. Yeah, I don't know if I answered your question,
Well,
but
you did. You did. You've laid out the case for it's important to address the spectral region with some high resolution spectroscopy. So thank
yeah,
you.
I think it depends what you want to do, right? I mean, if you want to look at very abundant gases, you can probably do that with filter radiometer. If you want to get to things like you know, diacetylene or methylacetylene, or, you know, trace gases, maybe, you know, benzene or methyl or something like that, you're probably not going to be able to pick those out of the spectrum very easily by doing a broadband filter. So you're going to have to go to, you know, to high resolution. And I think there's a lot of interesting chemistry, you know, that you can look at with a spectrometer, if that's, you know, if that's what you want to do. If you want to be able to tell Julie Moses, like, here's the real constraints on your model here, and here's data that you would need to constrain like a 2D photochemical dynamical, you know, like photochemical model with latitudinal mixing. You would need like mapping with high spectral resolution to do that.
All right, awesome. Yeah, and then in the chat, Catherine Elder chimed in saying, Diviner has 9 channels, two are solar channels. And it's also been about 15 years old, and we can do better now, but not a spectrometer.
Yeah, I mean, I really feel that every type of instrument has its place. You know, Diviner was a lunar instrument, you know, and the moon doesn't have an atmosphere. Not that I'm gonna not that I'm gonna consider an atmosphere anyway. So you're doing different science, right? You're doing mineralogy. Mineral bands are broad mineral bands. You could look at, you know, things like M cube as well, on Chandrayaan. So those are instruments that are very, very well designed and are perfectly suited to doing mineralogy, and maybe would be great for doing the moons of Uranus, or Triton, you know, maybe Triton or something. But if you want to do atmospheres, you're really in a different ballgame now. You've got narrow lines and you've got a lot of gases, and you can't disentangle those with that sort of instrument. So you need a different sort of instrument. So it depends what sort of science you want to do.
All right, great. Thank you. All right, a couple more questions here. So it's usually assumed that Uranus and Neptune have similar cores, but if Uranus and Neptune had different core compositions, do you think that could explain the temperature differences?
You know, I'm gonna punt a little bit on this one. It's a little bit outside of my expertise. I'm very focused on atmospheric science. I know a little bit less about the formation evolution scenarios. There's always been this mystery that Uranus appears to have a lot less internal heat that's coming out of it compared to the other three gas planets. And I'm just going to say, as far as I know, that's really not fully understood. You know, composition wise, they appear to be relatively similar in bulk composition. Definitely they're more similar to each other than they are to, you know, to Uranus, or sorry, to Jupiter and Saturn, which are, you know, really heavily hydrogen helium dominated. So there's a lot bigger ice fraction in those two outer worlds. But as to why the temperature differences, you know, yeah, I'm not able to answer that. Maybe maybe Mark or someone else has insights they want to share.
Yeah, if anyone does have any, you know, thoughts on this, feel free to unmute, comment on it.
Well, this is Mark, I guess. I'm not sure. I mean, a different composition might be able to explain it, but I also don't know enough to really. I think the core would have to be so dramatically different that it's an unlikely scenario. It's much more likely related to stability, or, you know, lack or inhibited convection at some point in the interior.
Yeah, I mean, I've always wondered just about the, you know, the really big difference in Uranus's obliquity, you know, its atmospheric tilt or its rotational tilt compared to the other three planets, and whether that is a factor in the fact that it, you know, appears different in other respects, such as internal heat. But yeah, that's about all I can say on that. I noticed some questions about instrumentation in the chat.
Yeah, so the next question in line is actually just that very topic. So similar question as Mark's. I'm sure we could do better, but what if we sent a copy of Sears? Is there a more recent flight tested FTIR? And I know somebody else posted in the chat some possible tests, mini tests, O tests, L tests, EMIRs are all FTIRs. So Connor, yeah, if you'd like to comment on that.
Yeah, so I know a little bit more about this area. So so I was involved in Sears. I was the deputy PI of Sears eventually. So Sears was, you know, it was a big and kind of heavy instrument. It was about 2.5 times the size of Voyager Iris. So this is part of the issue with these FTS instruments that were built at Goddard from the 70s through the 90s, is that they kept getting bigger and heavier. So because Cassini was such a big spacecraft and it had, had a lot of power, it was able to carry Ceres, which I think was around 43 kilograms, whereas the Voyager Iris was around 18.5 kilograms, something like that. By the way, there is a review paper that you can probably dig out, or I can send to people, which reviews all the different Goddard built FTS instruments. It's an IEEE paper, came out a couple of years ago. But the goal would be to try to get away from something like Ceres. So Ceres was really 2 interferometers in one, but certainly not 2 for the price of one. It was, it was 2 that shared a telescope, but then it had a field splitting mirror, and then it went into 2 totally different interferometers. So there was a totally different interferometer for the mid and the far infrared, and totally different detectors, totally different beam splitters, and that that enabled it to be a little bit better than Voyager Iris in some respects, but also at the price of being larger, heavier, more complex. So there's been some work done at Goddard to evolve Ceres back towards a smaller instrument, in particular, just having a single interferometer, which sort of cuts it in half again. But then you're faced with being able to have, detectors that work across the full range, or maybe different types of detectors. So there's other challenges that come up. But there's some work underway to try to shrink Ceres. And then there's some other examples of other FTIR instruments, particularly the ASU instruments, tests, mini tests, etc. And those were Mars. I think these are all pretty much Mars examples that are FTIRs, and they were really successful, but they're also designed to look at a much warmer planet. They use different detector technologies. They're looking at temperatures that are much warmer, typically 200 to 250 Kelvin, which is, kind of 100 Kelvin warmer than Saturn, and like 200 Kelvin warmer than the ice giants in the lower part of the stratosphere. So really, yes, all FTR technology is great, but you cannot simply refly a Mars instrument to the ice giants without just not being able to detect any radiation, because those detectors are less sensitive and a lot warmer. So you would need to change the technology, maybe put on a larger telescope than the tiny telescopes that were enabled on mini tests. And again, spectral resolution comes into play here. I think those worked at a slightly lower spectral resolution. When you want to go to, depending on spectral resolution, that influences things like your signal to noise that you get in your spectrum, your scan time, but also just the actual mechanical size, because you have to scan for a certain distance to get a certain amount of path difference. So those are all considerations. Having said that, I'm sure those instruments could be evolved to work for the outer planets.
Yeah, and it sounds like in the chat, Catherine was mentioning that there may be some evolutions happening in some of those instruments specifically for Uranus. Catherine, if you're willing to unmute and maybe
yeah, sure.
Sure, yeah.
I didn't want to take up too much of the time, but yeah, we have a Matisse grant working to basically design a new version of Diviner optimized for the Uranus system. And my expertise is not atmospheres. Armin Kleinball is the one doing that side. I'm doing the thermophysics, so I can't really speak to this talk. But it's definitely not a spectrometer. But we have been selecting bands, some relatively narrow, for different science goals in the Uranus system. And Daniel Wenkart is going to have a poster on it at the Uranus workshop next week, if anyone's interested. Yeah, and I guess my understanding is that the thermopile instruments like Diviner are better at cold temperatures than the bolometers. Yeah. Because yeah, as yours. Oh, and also to mention that MCS, which is very similar to Diviner, is an instrument at Mars that does Mars atmospheric science. So there definitely is history of these instruments being used for atmospheres as well. But I can't say exactly what it did at Mars because I'm on the Diviner team, but not the MCS team.
Yeah, and I'll just quickly respond to that. You're absolutely right. Yeah, that MCS was able to do atmospheric science. But there's a big difference between the Mars atmosphere to the outer planet atmospheres, and it's a much simpler in some ways atmosphere. It's really CO2 dominated. Um, not a whole lot else.
Yeah.
Whereas when you're looking at those complex atmospheres with all the organic chemistry, you're really sort of in a different ball game. I think you could do some of the more abundant gases like methane and maybe ethane. But if you want to get to all those like minor trace species, which you don't have on Mars pretty much, then you've got to go to a higher spectral resolution.
Yeah, that
But
makes
yeah,
sense.
by all means, yeah, if you just want to just put a band on top of CO2 and do that, you can do that. Yeah. Okay. See some hands up as well.
Yeah, I saw two shoot up, but I think I saw Elle first. So Elle, do you want to go ahead and unmute?
Yeah, thank you. I was wondering, because you mentioned a couple of times using millimeter wave spectroscopy, but I'm curious, how much does this science overlap between millimeter and far IR? I guess could you replace like could you just like do a millimeter instrument instead?
Yeah, it's a good question. So I actually do quite a lot of work with ALMA, so I do know the strengths and weaknesses of millimeter versus infrared. So a couple of things I'll mention. One is that in the thermal infrared, mid-far infrared, you're looking at molecular vibrations. So you're looking at things like bending modes of methane, bending modes of scissoring modes of methyl groups and all this type of stuff. That enables you to basically measure any molecule that exists basically. Whereas when you go to the submillimeter, you're looking at rotational lines. So a rotational spectrum, you have to have a dipole so that you can rotate and actually create an interaction with the radiation field. So you're limited to different types of molecules. If you look at the submillimeter, if you look at the submillimeter spectroscopy, you're looking at things like CO, HCN, isotopes of water, but many of the hydrocarbons which are symmetric, you actually can't see them. They're invisible in the submillimeter part of the spectrum. You can't see acetylene. You can't see ethane. You can't see methane. Although we've shown with ALMA that you can actually see deuterated methane if you look really hard because it's got a very tiny dipole. But yeah, you can't do all the same molecules. So if you wanted, it's great for certain types of science. If you want to do wind science and you want to track, just a half dozen molecules, or if you're really interested in looking at all the isotopes of water, all the isotopes of CO, you can do that type of science. But if you're looking at organic chemistry, not so good. The other difference is that with the submillimeter technique, because you're looking at this very, very, very high spectral resolution, they typically have narrower bands. And if you want to do multiple bands, you need multiple receivers. Now I know there's some technology under development that allows sort of tunable broadband receivers. But the band pass, I would say, can be an issue with a submillimeter instrument, depending on how you build it. And then maybe the third thing would be that, as you go to longer and longer wavelengths, you want to get a certain amount of spatial resolution. Just in your lambda over D, you've got to put a bigger telescope to get the same spatial resolution, or just fly closer. Yeah.
Thanks. Yeah. And then and Nancy, go ahead.
Hey, Connor, that was a great talk. Thank you so much. You actually started to answer my question with your final thought in response to the last question. And my question was about sort of any low-hanging fruit in terms of technology development for ground-based telescopes, which, of which there are relatively few that operate in the infrared region that you've been talking about. And, in the Northern Hemisphere, at least, the RTF's pretty small. But I guess, are there, in the event that it's too challenging or for whatever reason, these spectral regions aren't going to be possible to explore, from a spacecraft, are there things you could think of that would be a logical next step for ground-based facilities?
Yeah, and I think we're almost out of time, so I'll go pretty quickly. Let's mention a few things quickly. ALMA's great. Because it's so big, and even though it's at long wavelength, it does have good spatial resolution. There's upgrades underway to upgrade ALMA. We could also maybe talk about VLA, but with ALMA in particular, there's an idea that it'll eventually be extended by like an order of magnitude or more in size, another 300 antennas, and spill over across South America and just be a really big array. So there's things that can be done there. In terms of the infrared, one of the big frustrations that I have, and people know me, they know that I study Titan a lot, which has a really rich organic chemistry, is just parts of the spectrum that are blocked out from the ground. And no matter how sensitive your telescope, or how big it is, or what your spectral resolution is, if you can't get to certain parts of the spectrum, you're really kind of stuffed. Sophia provided some ray of light that we might be able to, get access to those parts of the spectrum. Unfortunately, that toy was taken away from us, but it also had its own challenges, which were tough. I think one of the interesting developments I heard about recently is a new infrared telescope, which is being built in the Andes by University of Tokyo. It's a 6.5 meter sort of version of IRTF, but it's also quite high, quite a lot higher altitude. You're talking about 5,700 meters, 18,500 feet. So about 4,000 feet higher than Mauna Kea, and maybe also has slightly better weather, precipitable water vapor. So that may enable us to kind of like narrow those telluric absorption bands. And I'm really optimistic we'll be able to, kind of encroach a little bit on that, maybe that CO2 part of the spectrum, but particularly like the 6 micron part of the spectrum where water is really obscuring. So I think there's some hope with ground-based, that we can do that. I also know, these big 30, 40 meter telescopes are being built. They are going to have some mid-infrared capability, but it looks like for now, looking at their sort of initial payloads, that they're going to be sort of more focused on broadband imaging or very low resolution spectroscopy. But hopefully they'll put some high resolution spectrometers on later.
Awesome, thank you. Yeah, we hit 12 o'clock, so right on time. That's perfect. So thank you so much, Conor. I really appreciate it. Next, looking at my, I won't blast up the community news slide just because we're out of time now, but just as a heads up, our June seminar is going to be canceled just because it overlaps with OPAG, and so hopefully we'll see many of you there. And then of course next week is the Uranus flagship workshop at Goddard just down the road. So we're really excited about that, and hopefully I'll see many of you there. But again, of course, excellent talk, Conor, and thank you so much for coming and presenting and sharing your knowledge. And thanks to everyone in the audience too for kind of contributing to this nice discussion. I think this was a great conversation. So
Thanks for the invite. Thanks for attending.
Definitely. Yeah. Thanks everyone. Bye.